In this video, we're going to take a look at adding and subtracting polynomials together. So before we actually jump into the adding subtracting process down here, we want to go through a couple definitions that we will see in this section, and we see quite a bit when we have polynomials showing up in problems. So we want to first define what is a polynomial. A polynomial is a very, very broad and far-reaching term that essentially means a monomial or two or more monomials combined by addition or subtraction. Now we need to also get the definition of a monomial in here. So a monomial is a polynomial with just one term. So we can kind of see where some terminology can get a little confusing with these a meal, like ones that we have in there. So let's take a look at, I think, some examples of what a monomial is right off the side here. So monomial is any number of things that is only multiplying together. So right under the monomial spot here, I'll put a few examples in if my screen doesn't want to, have pop-up show up with it. So some examples of a monomial. Well, just the number, let's say 5 or 3 could be a monomial. Maybe 35. We'll combine the numbers together. I'm thinking ahead of what I'm actually writing there. So the number 35 would be a monomial. The number -11 would also be a monomial. We could also have a variable thrown into the mix, maybe just the number, or the letter, I should say, x. And if we start combining variables and constants and things like that together, we can start to see some varying kinds of monomials. So we could have something like 2x or -3x, or we'll use y, and that just to show some other ones showing up in there. Now we can also have monomials that have multiple variables in them and even some maybe weird exponents as well. So something like 8x squared y to the third power. This whole thing, because everything in here is multiplying together, would be considered a monomial. We go with one that has 3 variables for the sake of one final example. Let's do 7a squared b to the third c. Why not? I have 4 things multiplying together here. The 7, the a squared, the b cubed, and the 3. Well, because they are all multiplying together, this whole thing is considered to be a monomial. And from that, if we go back to our core definition, a polynomial is a single monomial or 2 or more monomials combined by addition or subtraction, meaning I can have 1 or 2 or 5 or 10 monomials adding together here, and that whole thing is considered to be a polynomial in general. Now our 2 other main types that we have and we see terminology for on a regular basis is a binomial and a trinomial. A binomial is a specific type of polynomial with 2 terms, so 2 monomials, and those are adding or subtracting together. It doesn't matter if they're both adding, both subtracting, as long as I have 2 things that are adding or subtracting together. So a couple examples of binomials could be something like x plus 5, or -y minus 3, or x squared minus z squared. Or, again, we can go with any monomials like we saw up here. Maybe it's something like 3ab minus 10cd, something like that. But notice how each of these binomials has 2 things that are adding or subtracting together. It doesn't matter if one or both of them is positive or negative, but I'm only having 2 things that are adding, subtracting. That's the main staple of a binomial expression. And then a trinomial is the same idea as a binomial, except instead of 2 things, it's 3 things adding together. So a trinomial could be x plus y plus z. It could be, maybe we have something like 3a minus 9b plus 7. Maybe it's -4x squared plus 13y to the third minus, I don't know, 9xy, something like that. So we have three things adding or subtracting together with trinomials. So these are the three main terminologies that we're going to see show up the most when we are working with polynomials in general. There are terms for polynomials with 4, 5, 6, and terms beyond that, but we are not going to be covering those, and those are not necessarily common terminologies that we see in most problems. These are the main three that show up the most frequently. Now from there, we do have a couple questions that can show up and be asked where we're told to describe what is the degree of a term. So we need to make sure that we're being very specific here with the degree of a term versus the degree of a polynomial. They go together, but they are two separate things. So the degree of a term looks at one specific term inside a polynomial that might have 2 terms, 3 terms, 5 terms, or any number of terms there. And the way we determine the degree of that very specific term is the sum of the exponents of its variables, meaning we add the exponents of those variables together, and that tells us the degree of that specific term. So looking at some of the examples that we made over here off to the side, let's look at some of our monomials over here. What would the degree of this monomial be? Well, I would add the squared and the cubed together, so this monomial right here would have a degree of 5, the exponents adding together. What about this last one? I have an exponent of 2, an exponent of 3, and an exponent of, what's the invisible thing here? It's an invisible 1. So I would add 2 plus 3 plus 1. That gives me 6. The degree of this whole monomial, this whole term, would be 6. Now we can take a look at some of the ones down here as other examples. What would the degree of this term be? Remember, I'm only looking at this term, not this one. The term here, the degree of this one would be 2 because its exponent is 2. If I look at the other term, what is its exponent? It is also 2. So this one also has an exponent and a degree of 2 for this particular term that we're looking at. Now, once we have that, and we know how to determine those, the degree of an overall polynomial is just the highest degree of all its terms. So if I had, maybe I'll do a slight modification to some of these things that I have down here. Actually, we can just use this trinomial one as an example. So I'd look at a trinomial here and be asked, what is the degree of this overall polynomial? Well, I'd need to first know what's the degree of each individual term. So looking at my first term, I have x squared. That's the only exponent there, so the degree of this term would have to be 2. Looking at my second term, I have y to the third power. That's the only degree there, so that means this term has a degree of 3. Looking at my last term, I have x to the first power, y to the first power, and if I add those together, then I get a degree of 2 for my final polynomial. So a degree of 2, a degree of 3, and a degree of 2 again. So what is the highest degree amongst all of those in this trinomial? Well, it's going to be this 3 right here. And therefore, because that is the highest degree, the degree of this overall polynomial is going to be 3. This is something that shows up fairly regularly with this section, but it's not a big staple that shows up more too often beyond it. It is worth noting and seeing it a couple times, though. Now with that, all the preliminary definitions and things out of the way, we can go ahead and move on to actually adding and subtracting these polynomials together. The main thing that we are going to be using in the property that we are using with adding and subtracting polynomials is something called combining like terms. Now our definition for like terms is that the variables and the variable exponents in a term must be identical with one another. This part here, if you are writing this down for yourself, which I highly recommend that you are doing, put some underlines, put some stars by it. This right here is the make it or break it step with adding or subtracting polynomials and like terms together. They have to have the exact same variables in the terms, and the variables must have the exact same exponents for all of the variables. If even one exponent is slightly off from the rest, then I do not have like terms, and these things must stay separated from one another. If they do have identical variables and variable exponents, then we can add and subtract just the coefficients together. It's just the numbers out front, the big ones that are sitting in front of the variables. Those are the only things that will add or subtract or change in this process. We absolutely never, ever change exponents when we are adding or subtracting polynomials. It is only the coefficients that will be changing in this process. One other thing that I think is worth noting here, because this is what gets a lot of people in trouble, make sure that we are being very careful with distributing signs correctly. Negative signs in particular are big culprits that show up and make these problems much more difficult than they need to be if we are not correctly writing out and organizing our work and applying negative signs properly. A last thought that we can do, this is not required, but it is something to at least think on as we are going through these processes, and I think this will become apparent when we take a look at our examples. But it is worthwhile noting that you can rewrite and reorder like terms to be next to one another one step before you actually add or subtract them together to keep your work organized. This is entirely optional and not something that you need to do, but if you find you're getting confused with what can and can't add or subtract together, which terms are like terms, which ones aren't like terms, you're having some issues keeping track of it all, I think this is very, very useful to do just to rewrite it and make life a little bit easier for yourself before you actually combine like terms together. So let's take a look at these four examples here first and see some ways that we can combine like terms, distribute negatives, and maybe go through one or two routes of reordering these things to combine them together. Taking a look at our first example, we are given -4n to the third power plus 9n to the third power, and we are told to combine the following polynomials together based on the previous directions. So first and foremost, I need to check, do I have any like terms in here? Remember, that means they have the exact same variables and the exponents are the exact same as one another. So they both have n's, and the n's are both being raised to the third power. That means that these are two like terms, and I can add or subtract these things together. When I am doing that, remember that only the coefficients, the numbers in front, coefficients being the -4 and the +9, those are the only things that will be changing from this step to our next one. The n to the third power that we see in both of these terms will stay the exact same. Variables in their exponents absolutely never change when we are combining like terms. So I have an n to the third power, -4 plus 9. That's going to give me a +5. I don't have anything else that I can combine with this term right here, and therefore I have my final answer of 5n to the third power. In our second example, we're starting to see a little bit messier sets of stuff show up. So we have some prep work that we need to do before we actually add and subtract things together. So we are given the first polynomial to be 3x² minus 7y, and that whole thing is being subtracted by the polynomial -2x² plus 4y. Now we have parentheses showing up, and we have subtraction going on with those parentheses. We want to get everything outside of parentheses first and get those taken care of before I can actually add or subtract or combine any like terms together. So looking at my first polynomial, do I have any coefficients in front here, like a 2 or a 7 or a negative or anything like that? Well, at best, I could maybe say I have an invisible 1, that's in front there, which is technically there. And if I distribute that -1 through, is anything going to change in this polynomial? No, it isn't. So all I can do is bring these first polynomial terms down exactly as they are. And there's nothing wrong with that. We find on a pretty regular basis that that happens. Now the second polynomial, this is where we need to do some work. I have a negative sitting in front here. And then what invisible number is also sitting in front of that? It is also an invisible 1. So I really have a -1 that is going to need to distribute to every term inside this set of parentheses. So -1 times the first term, -1 times the second term. Let's extend that second line out here to show that just a little bit better. There it goes. So -1 times -2, that means it's going to become a +2. The x squared and the y stay the exact same. The -1 times 4y, well, it's a +4, so that's going to change to be a -4y. And again, the variable stays the exact same. Now that I have everything out in the open, there are no more parentheses showing up, there's no more negatives that are needing to be distributed, I can now go about reorganizing this thing and combining like terms through addition and subtraction. So we're going to, for this problem, show how you can rewrite these things to put like terms next to one another before we actually combine them together. This is an optional step. You do not need to do this, but consider doing it once or twice if you're having some issues or some headaches with combining like terms together. So I'm trying to determine what are like terms in this particular expression that I'm now working with. I see that I have x squared y, and I have another x squared y term. So these two things are like terms. I'm going to go ahead and underline those in blue, just for the sake of showing that they are the same. Do I have any other terms that are like terms as well? Well, I have a y here and a y here. Now both of these have y's, and my two blue underlined ones also have y's, so wouldn't they all be like terms? Not exactly. These two that have the blue underline, they also have an x squared attached to them. So while they all have y's, these two have an x squared with them, so those are like terms, and then the terms that only have y's are going to be like terms as well. I'm going to go ahead and underline those in red just to show that they are different. So now we can take a step to rewrite these things, and we're going to put the like terms next to one another. Make sure that when you are doing this rewrite, the sign, whether it be addition or subtraction, in front of that term moves with it. So this 3x squared y is going to stay where it is. I'm going to add plus 2x squared y, because I have my two x squared y's next to one another. Make sure we've got that sign carrying down. And then I'm going to have minus 7y, and then minus 4y. So I have my x squared y terms next to one another. We'll do those in blue again, just to see it. And then I have my y terms next to one another over here. And now it's very, very, very easy to see, hey, these are like terms. I can combine these coefficients together, and I'm going to get 5x squared y. And then with this last one, I'm seeing, hey, I've got the y terms. I can combine those together, and I get minus 11y. Remember again, when we are combining like terms, the variables and their exponents absolutely never change. It is only the coefficients out front of those variables that are eligible to be changing when we are combining like terms. Looking at our third example, we now have a trinomial plus a trinomial minus a binomial showing up in there. And this is really where the quote-unquote complications with these problems start to arise. We're just given more stuff that we need to add or subtract together, and just more stuff that we need to keep track of overall. Beyond that, there's not a whole lot else that can get really complex with these. We'll see in example 4 one last example of complication, but this is really just practicing our organizational skills. So I'm looking at my three terms here, and I'm noticing, hey, I have parentheses still. I need to deal with those before I can actually add or subtract these things together. So if you need to, remember we have invisible ones in front of each of these sets of parentheses. And we would distribute those ones through to everything inside of those sets of parentheses as well. So with our first set, if I distribute 1 through, nothing changes, so I can just bring down that polynomial exactly as it is. I'm pretty sure looking at the second one, yeah, it's also having a positive 1 distribute through, so nothing's going to change in that one as well. I'm just bringing it down exactly as it is. It's the last one that has a negative invisible 1 that's hiding out there, and that's going to need to distribute through to everything inside and change all of the signs inside of this last polynomial. So I'm going to end up having negative 2m squared plus 8 at the very end here. Now that I have everything out in the open, I don't have any more parentheses. Fantastic. I can now start looking for like terms to add or subtract together. For this one, I'm going to use what we did with our previous problem, which is just underline like terms, and we'll reorganize them once and then add or subtract them together. Again, you do not need to do this with your problems if you can keep track of everything, but it is something I recommend trying if you are struggling with keeping track of how much is going on in the problem. So I have m squared terms, 3 of them in this problem. And then I also have, looks like m terms in here as well. So I have an m and an m there. And then what else do I have? Well, I have these constants in here. These constants are just numbers. We can also consider them to be like terms as well. So let's go ahead and reorganize this. We're going to put all of the m squareds next to one another. We have 3 of them, so we should have 3 showing up. Whoops. This end part here. Let's go ahead and put the m's together as well. I've got 2 of those, so I should have 2 showing up here. Perfect. And then my constants at the very end. And the 3 of those there. And now that we have all of our like terms next to one another, now we can add or subtract the coefficients together and see what we get. So we have 1 plus 6 gives us 7, 7 minus 2 gives us 5, so we're going to have 5m squared for the m squared terms. We have 5 minus 1, that's going to give us a positive 4m, my m terms. And then for the last part I have with my constants, negative 2 plus 3, that's going to give me a positive 1. Positive 1 plus 8, that's going to give me a positive 9. And there I've just combined all my like terms that I possibly can with this particular problem. Final answer being 5m squared plus 4m plus 9. For our fourth and final example with adding and subtracting polynomials, we're given 10a to the 6th b to the 3rd plus b to the 3rd c as our first polynomial, and we are subtracting that by 3a to the 6th b to the 3rd plus 8b to the 3rd c. And again, this is very similar to our second problem. We just have a lot of variables and a lot of exponents showing up. When you are going through these, again, we do not care about adding or subtracting or changing the variables or exponents in any way, shape, and form. They will stay the exact same from the start to the end of the problem. So for starters with this, again, we have things in parentheses. We need to get rid of those. So we can fill in the invisible ones if we'd like to in front of each set of parentheses. The first polynomial is not going to change at all, so we can just bring that down exactly as it is. No changes there. With the second one, it has that negative in front of it, and that negative is actually an invisible negative 1. So that negative 1 is going to have to distribute through to everything inside that second set of parentheses. That's going to give us negative 3a to the 6th b to the 3rd minus 8b to the 3rd c. So both of the signs changed inside here because of the negative out front. Now with this step, if you wanted to, like we did with the previous problems, you could reorganize this by putting the like terms next to one another if you would like to. There's absolutely nothing wrong with that. Or if you're someone who can keep track of what we have and haven't combined together, you're more than welcome to do that here and just combine them and write the results afterwards. So I'm noticing that I have an a to the 6th b to the 3rd and another a to the 6th b to the 3rd term over here. So I can add these coefficients together. I have 10 minus 3, and that's going to give me a 7 for my coefficient. Remember, the a to the 6th b to the 3rd stays the exact same. It does not change when we are adding or subtracting like terms together. I also have a b to the 3rd c minus 8b to the 3rd c. So this first one has an invisible 1 in front of it, so 1 minus 8, that's going to give me negative 7. So I'm going to have negative 7b to the 3rd c here, which makes my final overall answer for this 7a to the 6th b to the 3rd minus 7b to the 3rd c. Bringing us back to our notes, we do have one final set of things that we need to discuss with this particular section, and that is evaluating polynomials. This is generally something that we do after we've worked with simplifying polynomials down like we did with our 4 examples that we just went through. But our process for evaluating polynomials is the following here. When we're given a polynomial and asked to evaluate it, we're going to plug in the given values to their respective variables, and then we're going to simplify and find our answer using PEMDAS. So we will be given some sort of a polynomial. It could have one variable in it, like we have with example 1. It could have 2 variables in it, like we have with example 3, or example 2, I should say. I looked at the 3 there. We could have 3 variables, we could have 5, we could have 10, any number of variables, it doesn't matter. The problem has to also tell us what is each variable going to be equal to. In the first case, n is equal to 2. In the second case, x is 3 and y is 10. Maybe we had something where we had the variables a, b, c, and d in a problem. Well, we'd be given, there's the polynomial, and we'd be told a is this number, b is this number, c is this number, and d is this number. They could be positives, they could be negatives, they could be fractions, they could be decimals, they could be zeros. But we need to be given a value somewhere for each of the variables. And the problem has to give that to you. All we're going to do is plug those values in. I recommend inside of a set of parentheses because negative signs, once again, will screw this up if you don't do that. And then we just evaluate and simplify everything down using PEMDAS, our order of operations, which I believe we covered in the Math 70 material, but we'll go through and I'll write that out as a quick refresher with these 2 examples. So let's dive into these and see how we go about setting those things up and actually solving them. Looking at our first example with evaluating polynomials, we are given the polynomial negative 4n to the 3rd plus 9n squared plus 10n, and we are asked to evaluate it for n equals 2. So the first thing that we are doing is we are substituting 2 in for anywhere an n shows up in this problem. Now when we are doing this, always substitute inside of a set of parentheses. If you do not do this, negative signs tend to give us a lot more headache, and they tend to be the reason, whoops, I should probably put a 2 in there. They tend to be the reason that we miss problems, because exponents and negatives play very differently if the negative is inside of parentheses or outside of it. So now that I have this substituted in for this 2 substituted in for n, I can go ahead and follow PEMDAS, our order of operations, to go through and get to our final answer. And I'm getting that my final answer, once I've fully evaluated everything, is going to be 24. Here we have the second example of evaluating polynomials. I'm given something that's a little bit more complex. There's a little bit more going on with it. We can still go through it the exact same way we did before. We're given 5x squared y minus 11y, and we're told to evaluate this thing for x is equal to 3 and y is equal to 10. So just like we did with our previous example, we're going to be plugging in and substituting in 3 and 10 for x and y respectively. Make sure again when you are doing this substitution, even if they're all positive numbers, doesn't matter, always substitute them inside of sets of parentheses. Once we've done this, we can now evaluate it using PEMDAS, our order of operations, to get to our final answer. And we are getting that our final answer, after we've plugged everything in and evaluated it using our order of operations, is 340. Bringing everything back together as a quick recap of what we went through in this video, we had our main definitions of what polynomials are and what monomials, binomials, and trinomials are. We had some quick examples of what each of those types of polynomials look like written out here. But again, this is not the limited amount of what they can look like. There's a lot of options between them. We also went through the degree of a term and the degree of a polynomial fairly briefly. I think you'll probably see one or two of those show up on homework or anything like that, but they're not particularly frequent, at the very least in my class. If you are watching this video and you're in my class, we're not going to see a ton of these beyond this section, maybe the one after it. We then went into actually going through and adding and subtracting polynomials together. Remember that the main property is combining like terms, and like terms are defined as having the exact same variables and the variables having the exact same exponents. We need those terms to be identical in those two requirements, otherwise we cannot add or subtract anything together. If they are identical, then we can add and subtract only the coefficients together. The variables and the variables' exponents absolutely never, 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 never change when we are adding or subtracting polynomials together. We then went through 4 examples of adding and subtracting those, keeping track of some sign changes that showed up in there. And then we worked with evaluating polynomials. We're going to be given something and we're given values for n, x, y, whatever the variables are, and we just plug those in and simplify things down using PEMDAS, our order of operations. So if you're looking for some additional practice with these, I have 4 written out here that you can go through. There are 2 parts to each of these. In the first part, you're asked to add or subtract the polynomials together, essentially combine like terms like we did with the first part of this video. And then in part B, we're asked to evaluate the resulting expression from part A for the given values. So add or subtract the terms together in the part A section, and then for part B, plug in the respective values for the respective variables and simplify things down. We'll scroll down here to our answers, and hopefully you're getting something that's the same as what we have written in down here. If you are getting anything different, I would highly recommend backtracking to see if you plugged in values inside of parentheses, and if a rogue negative maybe slipped through the cracks and somehow messed something up. That tends to be the main culprit with a lot of these problems, especially the evaluating sections. But with that, that is everything for our 6.1 material.